Hello everyone. Today I'm going to introduce our work, Moving Agents Information in Congested Environments. Planning paths for multiple agents is an important problem that arises in many real-world applications of multi-agent systems. Examples include video game characters, drone swarms, and warehouse robots. In many applications, it is important to plan collision-free paths for the agents. But it is also important to keep the agents in some formation while they are moving. For example, in the left figure, the video game environment, you might want to keep your soldiers in some particular formation to protect themselves. And for the drone application, you might want to keep the drones in some particular formation to maintain a good communication network. However, sometimes it's not easy to keep agents in formation. So in this example, the agents want to move from left to right, and they have to travel through this narrow corridor. When they are in the corridor, they cannot keep their desired formation. So they have to break their formation before they enter the corridor and reform it after they left. Similarly, for this example, the team of agents want to travel through this forest. And when they are in the forest, they cannot keep their desired formation. But they still want to find some formation that is close to the desired formation. Therefore, in this work, we studied the moving agents information problem, where we try to plan collision-free paths for the agents, and while they are moving, we try to keep them in formation as much as possible. Here is an overview of this talk. I will first give the definition of the moving agents information problem and show some related work. I will then introduce our novel algorithm swarm mappath. Last, I will show some experimental results. First, this problem is defined by an undirected graph and a team of agents, which each has a start and a goal location. So for example, here we have a 4-neighbor grid, and these 3 locations are start locations of the agents, and these 3 are the goal locations of the agents. And we assume that the time is discretized, and at each time step, an agent can either move to a neighboring location or wait at its current location. Our task is to find a set of collision-free paths, one for each agent, that moves the agents from their start locations to their goal locations. For the formation, we say the formation of the agents at some time step is specified by the coordinates of the locations of all agents at that time step. And the desired formation is specified by the coordinates of the goal locations. But of course, you can use some other desired formation if you want. We use this definition just for simplistic purpose. Sometimes, when the agents cannot stay in their desired formation, we want to find a formation that is close to the desired formation. And we use this formation deviation to evaluate how close a formation is to the desired formation. So here is the formula. This formula captures the least effort required for the agents to move from their current formation to their desired formation when ignoring obstacles on the map and the collisions between agents. And this formula, this equation can be solved in linear time. So a special case is that when the agents are staying in their desired formation, this equation will be 0. So now we can talk about our objective. So we evaluate a solution by the mix span and the total formation deviation. The mix span is the time step when the agents can reach their when all the agents can reach their goal locations. So we want to minimize the mix span so that the agents can reach their goal locations as fast as possible. The total formation deviation is the sum of the formation deviations over all time steps. And the small total formation deviation can lead to a formation that is close to the desired formation. Therefore, in this work, we try to find a solution that has near optimal mix span and has small total formation deviation. Our problem can be divided into two key tasks. The first one is to plan collision-free passes for multiple agents, and the second one is to keep them information. For the first task, it is similar to the multi-agent pathfinding problem that is widely studied in AI. They have many algorithms, and many of them are complete and optimal, which means they are guaranteed to find optimal solutions. But the issue is that these algorithms do not consider the formation at all. On the other hand, the keeping agents information task is similar to formation control in robotics. And so usually they use some simple and local optimization method to control to make the agents stay in some particular formation. A popular algorithm is called leader-follower method, where one chooses a leader among the agents and plan a single path for the leader. Then they ask the other agents to follow the leader's path and stay in formation. So the advantages of this algorithm is that they're really simple and run pretty fast. But the issue is that they don't have a solution quality guarantee. So sometimes they may find solutions that has long make span, and sometimes they may find solutions that has bad formations. And even worse, sometimes they may even fail to find any solutions. Therefore, we propose a new algorithm that utilizes the ideas behind both domains. And on the one hand, the new algorithm can find solutions that has near optimal make span and small total formation deviation. And on the other hand, we prove that our new algorithm is complete. So here is the idea of this algorithm. We will first choose a leader among the agents, just like the leader-follower method. We will then partition the leader's path into open and congested segments. For each open segment, we will use the leader-follower method to plan passes, while for each congested segment, we will use a multi-agent pathfinding method to plan passes. So let's look at the detail. The first step, choose a leader. The idea here is that we want to choose a leader and a path for it such that if all the other agents follow this leader's path, in most cases, they can stay in their desired formation without colliding with the obstacles. Therefore, for example, if we choose agent 2 as a leader, and if this is its path, then we will check at every location along this path whether the other agents can stay in their desired formation or not. So for example, here at the beginning, if agent 2 is here, then agent 1 and 3 will be here, and they are okay because they don't collide with any obstacles. Then agent 2 move to here, agent 1 and 3 will be here, which is also okay. Then agent 2 moves here, and now this time agent 3 collide with an obstacle. So it's impossible for agents to stay in their desired formation at this time step. And we call this location as a formation blocking location. Then we just try the next time step. This time step, agent 1 collided with the obstacle. So it's also a formation blocking location. And this one, also a formation blocking location. And this one is okay. And the rest locations are all okay. So for this path, we will find 3 formation blocking locations. And we see that, okay, the number of formation blocking locations for this path is 3, and we will use this value to evaluate how good a path is. Therefore, we will first run a search algorithm to find a short path that minimizes the number of formation blocking locations for each agent. For example, this will be the path for agent 1, and this will be a path for agent 2, and this will be the path for agent 3. And then, after we get a path for each agent, we'll compare these paths and choose an agent as a leader whose path has a minimal number of formation blocking locations. So here, agent 1 has 4, and agent 2 has 3, and agent 3 has 5, so agent 2 will be the leader. The next step is to partition the leader's path into segments. Assume that this is the leader's path we found, and we mark the formation blocking locations in red, and we use green to represent the rest part of the path. So for each red part, we call it a congested segment, and for each green part, we call it an open segment. So for each open segment, we know that the agents can stay in their desired formation without colliding with the obstacles. Therefore, we just ask all the agents to follow the leader's path in the desired formation, just like the leader-follower method. For each congested segment, the agents cannot stay in their desired formation. So we call a modified multi-agent path-finding solver to plan collision-free paths for each such segment. So here is a detail. So for the previous example, we already know that these three are the formation blocking locations. So they consist of a congested segment. Now what we do is that we look at the time step before this congested segment and the time step after this congested segment. And we know that for these two locations, the agents can stay in their desired formation. Then we will use these two locations to form a sub-instance where we want the agents to move from here to here. And we will use a multi-agent path-finding solver to solve this sub-instance. In the paper, we propose an algorithm called CBSM, which is a modified CBS algorithm to solve the sub-instance. So CBSM is guaranteed to find collision-free paths with a minimal mixspan, and it breaks ties by preferring paths with smaller total formation deviations. After we got a path for this sub-instance, we concatenate all sub-paths from all sub-instances, and then we will get a final overall paths for the problem. Now let's look at some experiments. So we first test our algorithm on the random map. And you can see in this demo, so in most cases, the agents stay in their desired formation. And sometimes when some agents encounter the obstacles, the agents will change the formation a little bit. Note that although the agents can move up, down, left, and right, but the orientation of the formation will not change. We also test the algorithm with more agents and compare it with CBSM. For the mixspan, because CBSM minimizes the mixspan, so this is an optimal mixspan. But for our algorithm, we will find a mixspan that is larger than the optimal mixspan by about 20%. However, for the total formation deviation, our algorithm generates the total formation deviation much smaller than CBSM. So it improves CBSM by a factor up to 7. And then for the runtime, both algorithms run pretty fast and their runtime are close to each other. So for number of agents smaller than 30, our algorithm can solve them within a second. And for 40 agents, we can still solve it within 10 seconds. Next, we also demonstrate our algorithms in a simulated game environment. Here, we assume that there's a player who updates the goal locations every 12 time steps, and the agents keep moving follow the goal locations. And again, you can see that when the agent travels the narrow corridor, it will change the formation, but once it leaves the corridor, it will reform to the desired formation. To summarize, in this work, we studied the moving agent information problem, where we try to plan collision-free paths for multiple agents and keep them information while they are moving. And we propose a new algorithm called Swarm MapF, which is a complete algorithm that guarantees to find solutions. And we show that Swarm MapF produces solutions that keep agents information better than the CBSM, with only a small loss of optimality in mixspan, and we show that it can scale up to 40 agents. And that's all for this talk. Thank you for listening.